Okay, welcome back, everybody. I hope you all had a nice spring break light and got a little bit of a breather in the middle of the semester. Can everybody hear me okay? Okay. So today we have two parts of the lecture. First, I'll wrap up what we had planned to do last lecture but didn't get to, decision trees. And then Anna will take over and she'll talk a little bit about support vector machines, which is another classification method. But let me quickly recap. Like last time we talked about classification, and like to distinguish between classification and regression. In classification, we try to predict a categorical variable. In regression, we try to predict a real value. We mostly looked at binary classification, but I got a question on Slack whether we can do this for multi-categorical classification. And in fact, this works just as well, right? I can have like 1 or 2 or 3 or 4 or 5 or 10 different labels, and this works just exactly the same way as doing it with like a single binary variable. And then we talked about the KNN method, the K nearest neighbor method. And here the idea is really that you take K, like a number of elements, and let them like find out which are the closest K points to a pointer that you want to predict, and then let them vote on the class. And we talked about a couple of different variations of this. And then we talked a little bit more about how can we evaluate a classification value method. So we talked about like the confusion matrix, which is kind of like a very precise way of evaluating the results of a classification. And then we had talked about precision and recall, and then some other metrics like the F measure or the ROC curve or the Jacquard similarity score. And we talked about that scikit-learn provides all of this information. One thing that you should be aware of is especially accuracy scores tend to be a little bit like you have to think a little bit about how you interpret them, right? So let's suppose you have a binary classification, like a binary variable where you have 50-50 distribution in your data set. Then getting an accuracy of 90% might be pretty high. But if you build a model where you have like very rarely only one particular variable, let's say 10% of your values are only of like one type, then getting a 90% accuracy isn't actually that hard, right? You just always predict a more frequent variable. So like, especially if you look at accuracy scores, you have to judge a little bit and think a little bit more about what the accuracy score actually means. And also like accuracy scores, if you have non-binary, like let's suppose you have 3 variables that are equally distributed, like your accuracy is likely going to suffer, right? Because like if you just randomly predicted a category, you would get like something like 1/3 of the values correct. So it gets harder the more classes you have. Let's see, is there anything else I wanted to talk about? Yes. We talked about cross-validation and model generalizability. And so the idea here is that we want to do splits of our data set so that we can like separate a training data set from a test data set, because we want to also measure how much we overfit and if we overfit. And there's like, you can also use kind of cross-validation to find parameters. So you can try out, like we did here, for different Ks, run the classifier, and then pick the K with the best accuracy. And generally, we have this trade-off between like the model complexity and how the more complex the model, the more it tends to overfit. So we have to find like a good model that is of medium complexity and has low prediction error. That's usually the goal in many machine learning applications. Okay, so let's talk about decision trees today, unless there's any questions about what I just said. Great. So decision trees is like a second classification method, which you can also use for regression, but mostly we'll use it for classification, which is also super intuitive, just as intuitive as k-nearest neighbors. You have a couple of things that you need to install here, like both of these packages, and I know there were some issues with installing this, but those are really only important for like visualizing the decision trees. You don't actually need them to do classifications with this decision trees. Okay, let's look at what a decision tree is. Let me just clear my outputs here. Okay, so what we'll use an example of a data set of Titanic passengers, and we'll try to develop a model that predicts whether a particular passenger will survive or not. Clearly, like intuitively, it doesn't, like the variables we have here, like passenger ID, here we have our labels, survived, the class of in the cabin, the name of the patient, and their sex, their age, whether they had siblings or spouses on board. Like this is a numerical value here. So this means this person had one sibling or spouse on board, but there's some cases where you have like 8 siblings or spouses on board. PR, just the number of parents or children aboard. You have like a ticket ID, you have the fare paid, you have the cabin number, and you have the embarkation point. And here they are: Cherbourg, Queenstown, or Southampton are the 3 different embarkation points. And just like intuitively, do you think there is a machine learning model out there that can take those variables and 100% accurately predict whether somebody survived in a Titanic disaster? I see a shaking head. So yes, this isn't something that we can, like, we don't have enough data. There's like lots of factors where people were located on the boat, for example, that will influence that. So we can't expect that we get this 100% correct from the data we have. But intuitively, it also makes sense, right? Especially given social convention, we would expect children to survive more frequently than adults. We would expect women to survive more frequently than men. And maybe there is an effect of class, right? Passenger class, like people maybe in first class were prioritized in rescues, or maybe people in first class were in higher decks and had an easier access to the boats. Maybe something like this is happening here. So we want to use this data set to predict survival. And now let's look at how could we do this with a decision tree. But first, like, what is a decision tree? Decision trees are these very intuitive classification and regression tools. And like you can actually use them for simple decision making. So like, for example, the New York Times built a decision tree which predicts whether a county voted for Obama or Clinton in a 2008 Democratic primary. And you kind of like get these questions. Is a country more than 20% Black? Then yes. If you make the decision here in this tree, if this is true, then this county has a larger African American population, and Obama wins these counties 383 to 70. If the answer to the question is no, we go to the next question. And that's kind of like the essence of decision trees. So we ask subsequent questions about the data set. So here would be the question: is the high school graduation rate higher than 78%? If the answer is no, then this is a county with less educated voters, and Clinton wins these counties. And we can keep going like this. And so applying a decision tree is very, very easy and very, very intuitive. Here would be like a decision tree based on the survival of passengers on the Titanic. So for example, if you have the is sex male, then the answer is no. Then we predict that the passenger has survived. And this is actually like correct with like 73% accuracy. If sex is male, then we have to make a further decision. If the age is bigger than 9.5, then we predict that this person is tied. Then we keep going. Is sibling or spouses greater than 2.5? If that is true, we predict that the person's died, or else we predict that they survived. So this is just as simple as above, but just like applied to this particular data set. So we would just really like can use these very, very easily and intuitively. So the question is really, how can we build such a tree? And it's really not much harder than reading one. There's like an algorithm that's called the ID3 algorithm. I've linked the description here on Wikipedia. But intuitively, it has a couple of steps. If all the data have the same label, you create a leaf node that predicts that label, and you're done. If the list of attributes is empty because maybe you've used all of them already, create a leaf node that predicts the most common label. Else partition the data by each of the attributes and choose the partition with the lowest error. This is kind of like the key sentence here. So if we have like a vector and of data with labels, we can look at all of the attributes and find the one that partitions the data with the lowest error. And that's the one we pick. And then we can recursively continue on each partition subset using the remaining attributes. And then we end when there's no attributes are left, or when we have reached the termination criteria, such as like a maximum depth or a minimum split size. Here's like a super nice interactive tutorial that I want to walk through quickly, but you should also like play around with it on your own. And so this is from like a series of like R2D3. They've been kind of doing some like explaining machine learning with visual means. And so here we have a data set where we have like housing prices in San Francisco or New York. And now we want to be able to classify whether a particular home is on the market in San Francisco or New York. And so we would have like one of the attributes in this data set is the elevation of the home. So we would have like homes at an elevation of 744 feet, which looks like San Francisco, because San Francisco is hilly, New York is actually flat and close to sea level. So we wouldn't expect there to be like high elevation homes. So maybe we can say that like homes that are like high in elevation tend to be in San Francisco. But similarly, we can say that New York City apartments are more expensive than San Francisco apartments, at least in this data set. And so we could say that homes that cost more than $1,700 per square feet are in New York City. So we can like identify these boundaries and create these splits. And the data set we have here has elevation, year built, the number of bathrooms, the number of bedrooms, the price, the square feet, and the price per square feet. And so if we want to like use decision trees for this, we kind of can look at this and then create forks. These forks are really what makes these like these branches in the tree. So we would say that if we look at elevation here and try to like have a perfect fork for at least predicting the San Francisco point, like these split points, we say we only include homes that have 242 feet of elevation or higher. And that kind of accurately classifies all of these San Francisco homes. So there's no misclassification of New York. But in this, like when we predict New York, we actually misclassified 92 San Francisco homes. So this is like a split point, but it's not necessarily the best split point possible. Like it doesn't necessarily minimize overall error. So maybe because this seems to be an outlier, maybe it would be better to have a split point around here, right? So if we like moved the split point to 0 feet, we get a lot of false negatives. But if we like try to find the best split, we like that would be somewhere at 91.9. Here we have some false positives for San Francisco, but overall the error here is minimized. And then we can do this for all of these different variables here. So we can say price is the next factor, price per square feet is the next factor, and then we can like create this tree, like first elevation. Then if it's lower elevation, we do price per square feet. If it's higher elevation, we do price, and so on. And so we can build up this decision tree. And we have like a deep tree now that perfectly classifies our data set. So in this case, we can actually do that. The problem, of course, is that here we might, like, if we just do this on, like here we're making predictions. So we are running all of these kind of like each of these balls here corresponds to like one of the homes. If we run this through our decision tree, we can see that we get like perfect classification, 100% accuracy, but of course only on a training data set. And so what we see here is already like the tree is very complex. It can completely describe our training data set, but maybe for test data, this doesn't work quite as well. So this is where we measure the performance of never before seen data. And we can see that our test accuracy is much, much lower than our training accuracy by like about 10%. And so what happens here is like in KNN, if we had a very low K, if we have a very complex tree and hence a very complex model, we tend to overfit our data set. So, okay, so like the position with the lowest error, that's kind of like the challenge, the most important thing to come up with in building a decision tree. And so what you would do is you can write this like this. We can have our variables x, I, and p, where you have I for passengers and p for predictors. For the first split, we would consider all the passengers and all the predictors. And then we also have observed labels, y of I for each passenger and predicted labels of y hat of I. And we can calculate the mean error by simply doing like the sum for all of the elements with L, which is our error function here of y hat and y. And the error function could be something like squared error for regression, or we could use something like cross entropy or the Gini impurity for classification. And if you're interested in these, I would just like urge you to look them up individually. But essentially, we need some kind of error function to determine that. And then we want to achieve two things. We want to pick the best split for the best predictor. And so what we do is we consider a list of all possible decisions or splits. So for like integer values, we try all possible different splits. Of course, you don't actually do all possible different splits. You use some kind of heuristic to do that. And then for each possible decision, we recalculate the prediction for that rule. And then we recalculate the mean error for each possible decision, and we choose the decision that reduces the error by the largest amount. And then we continue the next step on the reduced input set. So for example, in our previous example, if we take elevation first, we would remove elevation from our consideration. So as I already said, it's easy to overfit the data, and there are several methods for avoiding this, which we'll discuss below. And like just as a preview, simple strategies include limiting the depth of a tree or only splitting when we have more than n samples left. So let's talk about how we do decision trees with scikit-learn. I'm reading the Titanic dataset here again, and I'm doing some data cleanup. Age has some missing values. Like I'm assuming here that the person with missing age is of mean age, which might not necessarily be a good decision. Embarkation point has missing values, so we will just add a dedicated category for unknown embarkation points. And then we need to convert the categorical variables to numerical values because scikit-learn requires these to be numerical dimensions. This is what we're doing here. And then we will kind of like omit passenger ID, name, ticket, and cabin because these are not, they might contain some information, but they are labels more or less. And they don't like they're not easily converted to like numerical categories, and they don't like naturally make sense. So if we look at this now, we can see that we have like survived has a mean rate of a mean value of 38, so 0.38. That means 38% of passengers on the Titanic survived. Our mean class, like first class, second class, and third class, is 2.3. Our mean sex is 0.3. We have labeled males as 0 and females as 1. So what it means, we have more males than females. Our mean age is 29. We have 0.5 sibling spouse, and so on. And we can look at this in a scatterplot matrix, as we usually do. This will render in a second. And so here, the scatter plots themselves are actually not all that informative, but what we can see, like survived, the blue here is 0 is died and 1 is survived. So what we can see here roughly, like the first thing here is class. We can see that people in third class, the blue KDE plot here, died very frequently. People in first class, more people in first class actually survived than they died. If we look at sex, we can see that women were more likely to survive than die, whereas men were much more likely to die than survive. And then for this column here is age, we see there's this little bump for age, so that kind of like means that many children actually did survive, but also many children did die. So it's not a, like, obviously not a perfect prediction, and so on. So you can look at this, and there you'll find other little interesting facts about this data set. Just as a side note, another way of looking at these categorical types of data is this parallel sets technique. Like, you can play around with an interactive version here, but that just shows you kind of like ribbons of like, what are the attributes, the categorical attributes of people that survived or perished. So you can see that like females, the more than half of females survived, and like only about a third or a quarter of females died. And for children, we can see that like a good chunk of them actually did survive, and so on. So now let's build our decision tree. First, I am just creating this is some code that does our data set splitting into training and test sets. And then we have here some more code for plotting decision trees. These are just two functions that I will be used subsequently. And now let's look at the decision tree that only separates on sex. Okay, so if we do that, we get a decision tree with an accuracy on the training data set of 0.81 and an accuracy on a test data set with 0.76, which is just using a single variable is actually already pretty good. And we've already learned earlier that sex is actually a good predictor. And so you can like read this this tree now. If sex is smaller than 0.5, then predict perished, and then you get like how many people were correctly classified and how many people were incorrectly classified. So we have 245 correctly classified and 43 misclassified, and the color coding here also is used to kind of like give you a sense of how accurate how accurate this class represents this node. So you can see like the darker this is, the more accurate this is. So we have like overall 76% accuracy, which isn't all that bad. Now let's add more features. We can add the number of siblings and the spouses as features. Here I'm just like extending the used features. I'm using this for my split function. Then I'm running my decision tree classifier with my training and my training attributes and my training labels. And then here I'm predicting it. And then I'm just doing the metrics and rendering the tree. And so now with these features, what we see here is we get like a much more complicated tree already. And our accuracy on the training set has gone up to 0.83, but our accuracy in the test data set hasn't gone up quite as much. So we have actually lower accuracy, slightly lower accuracy than we had before on our test data set. So clearly we are already overfitting our data. And so here, like, we're splitting first again, not surprisingly, the decision tree decided to split first by sex, and then decided to split by sibling spouse smaller than 2.5, and then a sibling spouse smaller than 0.5, and so on. And so you can see that we have, even though we have these like classes that are all essentially predicting that they're perished, we still have these leaves here that give us divide the data set further. So clearly we've overfitted. Let's just try this thing with all of the features: class, sex, age, sibling spouses, parents or children, fare, and then embarkation point. And if we do that, we get a pretty complex decision tree with a very high accuracy on our training data. And like here, we can't actually see the labels anymore because the decision tree has become so complex. But the accuracy on the test data has actually gone down. So now this is a worse decision tree on the test data than just splitting by sex, right? So clearly, this isn't great. We are overfitting the data. So we have created an overly complicated model. And now let's look at how we can avoid this overfitting. We can use two parameters, the max depth and the min sample split. The max depth essentially tells us don't make your tree deeper than 3 levels or 4 levels or n levels. And the min sample split is either a number or a percentage of how many values you should have at least in a node before stopping the split. So you could say, I want at least here 10 samples. And if it's less than 10 samples, stop splitting that node. That also kind of like limits the depth of the tree, but it doesn't do it kind of like in a hard way, like you may at most be 3 levels, right? So the trees will get deeper if I just use a min sample split than using a max depth, but you will also reduce the splits. And so let's explore those two options. If we limit the depth to, in this case, 3, as you see here, we are actually getting a much better accuracy. We're getting like 0.79, so like about 80% accuracy on our test data set, though we're still overfitting because we have like much better accuracy on the training data. And so this tree here is now like easy to read again. And then if we use the limit, we limit the minimum samples we use to split, that works as well. And now we get a deeper tree, but as you can see, it's much easier than the one we had earlier, so you can still read this. Our accuracy is higher than the 76%, which is our benchmark more or less, but we're still overfitting. And so if we try to limit both, we get an accuracy about 80%. This looks very much like the depth here is dominant. And so yeah, we can like again use something like cross-validation to find ideal parameterizations of this. But yeah, like having increased our accuracy by 4%, that sounds not like that much, but in classification, improving your accuracy by 4% is actually quite a lot. So this last model here is fairly simple, yet quite accurate. The main points here are that sex is the dominant factor at the root of the tree. For females, if you're in class 1 or 2, you're almost sure to survive. For males, if you're younger than 6.5 years old, you had a chance to survive. And there are some branches that predict the same thing, but with different certainty. For example, in the male adult category, if you were in first class, you still were more likely to die than not, but you were less likely to die than if you were in second or in third class. OK, so here, like some discussion about decision trees. So they're simple to explain and interpret. They're like the poster child of explainable machine learning, right? If you were to implement a decision tree in, let's say, an emergency room to diagnose where somebody had a heart attack, then you could like have these very simple decisions to be made. They would probably make clinical sense to physicians, and they would trust the model, which is not always the case in machine learning models, right? It's like easy to interpret. And if you think about credit decisions or medical decisions, this is a property that you really care a lot about. We have these nice graphical displays for the trees that make them even more easily to interpret. And they can also easily handle categorical predictions. So for example, we had our embarkation points or passenger classes. Though like that's actually true for decision trees in general, scikit-learn doesn't really support categorical variables, unfortunately. So we always have to kind of like translate this to numerical encoding. And so what we did earlier is we encoded all these embarkation points as 0, 1, 2, 3, or 4, which is actually not a good thing for decision trees, because here, like embarkation minus is smaller than 0.5 is not all that meaningful, right? Like these are not ordered; they're purely categorical. And so what we should have done instead is an approach that's called one-hot encoding, where we create like a new dimension just for like one label in the category. So entered in Cherbourg or not, and then entered in I forget what it was, but whatever, this British town or not. So you create, instead of having one column with many categories, you just create like one binary column asking like for, is it in this category or not? And then you can use the scikit-learn decision trees very effectively here. This has some other disadvantages. It makes your data set bigger and a little bit more complicated. But generally, that is a way of doing it. And other implementations in R, for example, don't have that limitation. They can actually work with categorical data. A disadvantage of decision trees is that they generally don't have the accuracy of other approaches, as they tend to overfit the data, and they're like not robust. They're sensitive to small changes in the data. But there's methods that we can use to address these disadvantages by using what's called ensemble methods. And this is only going to be like a short detour. I want to briefly talk about ensemble methods, but first, are there any questions about decision trees? Well, if not, so as I said, one of the downsides of decision trees is that they tend to overfit. And a way to tackle this is called this method, this more general method that we can also use for decision trees of ensemble methods. Here we use multiple algorithms at the same time, and like maybe different configurations of, let's say we create 10 decision trees with different parameterizations, and then let all of these 10 decision trees classify the same data and then let them vote. That's kind of the idea of ensemble methods. There's two very common methods. The one is bagging, bootstrap aggregating. And the idea of bagging is to generate several trained models based on subset of the data and let the decision, like you take essentially like 60% of the data for tree 1, another 60% that you selected for tree 2, another 60% that you selected independently for tree 3. And commonly, the subset is chosen through bootstrapping, so random sampling with replacement. If we average a set of observation, this reduces the variance. Think of the central limit theorem. This increases our predictive accuracy of the method. And like this is bagging, and boosting is similar to bagging, except that the trees are grown sequentially, and they're trained specifically to address misclassified items in a previous tree. And if you apply any of those two methods to decision trees, it's usually called random forests. So random forests, the funny take on like multiple trees are a forest, of course. And random forests combine multiple decision trees with some randomness and then let them vote on the result. And a random forest used to be kind of like the state-of-the-art technique from like about the time when I did my PhD. So in 2012, lots of computer vision happened with random forests. Now this has been replaced mostly by neural networks, but they used to be like a very reliable method. And so if we do this on our data set here, a random forest, we can get like an accuracy for this data set that is not much higher, but like we're actually not limiting our decision trees in any way. Like we're not limiting depth or split size. And we get like to an immediate accuracy of about 80%. And so in a bigger data set, we would expect that the random forest would have like a bigger effect. So generally, ensemble methods are of higher accuracy. And the obvious drawback, of course, is like creating 300 trees is like 300 times more expensive than creating a single tree, right? And also making a decision based on 300 trees is 300 times more expensive than doing this on a single tree. Okay, I'll take any questions you might have while Anna is getting ready to take over.
A quick question, kind of small. Why does the training data give such better accuracy with these models than the test data again?
Well, that's because for the training data, we built the model to explicitly fit that training data set, right? So let's suppose by chance we picked a data set where like the age of 6 perfectly splits your like data set into survived or died, right? But that might not hold for the general data set, right? That might just be a random artifact for this particular subset that I used to train it on. So I can optimize my algorithm or my machine learning model to really fit perfectly to our training data set. And that problem, like that, just like that, these kind of like very specific decisions that you make on one data set, they don't generally hold necessarily for other data, right? And so if I have like a randomly selected subset, that might not be that at the age 6.6 is exactly like the perfect dividing line. Maybe it's 8 in the different subset of the data set, right? And so that's why the models usually perform better if they're, especially if they're overfit way too much. They perform perfectly on the training data set, but on the training data set, but don't perform as well on the test data set. Of course, what you really want to do is you want to build a machine learning model. Like training and test splits are just used for like building and evaluating a model, right? But in real life, you will see never encountered data before, right? Like you will see something like you get an image and you want to classify what is it, but you have never seen that image before. And so like you need to kind of like have a model that generalizes to this particular image, and it's unlikely that a model that is very overfit will do that.
Okay, that's great. Thank you.
I have a question. When you limit the max depth, is that like a branch and bound where you pick a classifier, go down a level, pick another classifier that exceeds the max depth, so you have to bounce up a couple levels to change the classifier to maximize the classification with the depth?
That's not usually done, and I'm not sure it would help much, because like you're like at every point you're making the best decision you can, right? So like at level 1 you're making the best decision that is possible for the data set. At level 2 you're making the best decision that is possible for the remaining set. Of course, there could be situations where level 2 splits would be better than if you had taken a different level 1 split, but that generally doesn't happen with decision trees. So there could be some artifact if you limit the depth like that.
So it's just
Or
when
decision.
you trained on 2 classifiers, it performed poorly, but when you limit the depth, it performed better.
Yes, on the test set, right? It didn't perform better on the training set.
Yeah.
Yeah. Okay, with that, I'll hand it over to Anna.
Okay, sounds good. I guess we can give everybody 5 minutes for a little break and come back at 1:08, and then we'll talk about SVMs. So I'll see you back in 5 minutes. Okay, well, it's 1:08. I guess we are back from our break. Hello, everybody. I also hope that you enjoyed your little time off last week. Okay, so to be continuing the discussion of classification. So remember, just to put it in context, in the regression context, we're trying to predict a quantitative variable, but when we're trying to predict a categorical variable, we call this classification. So we've already talked about the k-nearest neighbors classifier and decision trees, and more that we're going to talk about, which is support vector machines. These methods are especially good at classifying medium-sized complex data sets, and they're actually very popular. So it's a really good tool to be familiar with. And the idea of support vector machines is to use tools from optimization to find the best lines, or more generally, in higher dimensions, hyperplanes, or if we're using a certain kernel version, these planes can become curves that divide the two data sets. So we'll start off thinking about the simplest version, which is two classes. So we have, the binary case and no kernel transformation, or sometimes this is called a linear kernel. So let's suppose that we have n samples, x1 through xn, and also their corresponding labels, y1 through yn. So the x's are the attributes or features, and then the y's are the categorical variables which we want to predict. And so the x's, so think of those as a vector because it could be a large collection of features. And the y's, we'll assume they're either 1 or -1, indicating the class, right? Male, female, true, false, whatever variable of interest. And so we want to, the idea behind support vector machines is to find a line which separates the two classes. So here in the picture, you can think of the black points as having label 1 and the white points as having label -1. And we want to find a line that separates the classes. And what do we want to be true about this line? Well, we want it to have as large a margin as possible, where by margin, we mean distance from the line to the closest point in the other class. Okay, so this is called finding the maximum margin line, or more generally, the maximum margin hyperplane, which is defined so that the distance between the hyperplane and the nearest point in either group is maximized. Okay, so we have another question here. How is this different than a logistic regression? So good question, and we were hoping to talk about logistic regression in class, and we ran out of time, but it has the same goal. It's another way of predicting a class, so of doing classification, but it's a different method. So so we won't really have time to go into the details of that, but it's just a different method for classification. Okay, so this is kind of the picture to have in mind. You can kind of work, there's a little calculation to work it out, but so this middle line is W, the inner product of W and X minus B equals 0. And then this is the line inner product W and X minus B equals 1. And this is the line inner product WX minus B equals -1. And a little calculation can work out that the size of the margin of the distance from this middle line to an outer line is 1 over the of W. Okay, so remember that you can write the equation of any line as the set of, in this way. So, a lot of times we think about a line as y equals mx plus b, but this is another alternative formula that's a little bit easier once we start to get into higher dimensions, is to think of a line this way. And the goal here is to figure out, well, what's the best W and B? Once we fix W and B, we fixed our line, and that determines our classifier. Once we found good values for those parameters, W and B, we can build a classifier simply by mapping X to the sign of the inner product of W and X minus B. Okay? Okay, so that's the idea. And we'll start off with the hard margin case, even though that's not what we usually do in practice, because usually data is not perfectly separable. But if we go with a hard margin, then if the data is linearly separable, then we find the separating line or plane with the largest margin, which is this 1 over the norm of W, right? So that would just be the distance from here to this closest point. And this is given by solving the following optimization problem. We want to minimize the norm of W squared, right? So you can think about maximizing 1 over the norm of W is equivalent to minimizing the norm of W. So we just kind of flipped the problem around, and we're going to solve it via a constrained optimization subject to the following constraints: that yi times the inner product of W and X minus B is greater than or equal to 1 for all of our points. So, if you look at this constraint for a second, think about, okay, if I have a point that has label 1, then the inner product of W and X minus B with that point, this will come out to be. On the other hand, if I have a point with a label of -1, then this, comes out to be a -1. You multiply -1 by -1, which gives you a +1. So actually, this constraint is ensuring both that the +1 points and the -1 points do not fall inside that margin. Okay, and so we talk a whole lot about the details of solving this optimization. But if you want to know more, take a class on optimization. It's a hard and interesting and useful subject. But in this class, we'll simply, stick with our built-in tools from scikit-learn and Python. Okay, so from the picture, you can see that this max margin hyperplane is determined by the points that are closest to the separating lines. Okay, so this is this point right here. So you see how this black point is the closest one to the separating line. And then on the other side, it looks like we've got 2 white points that are equally distant to the separating line. Those are the points that are really driving the classifier in this hard margin SVM, and they're called the support vectors. So these 3 points are called the support vectors because those 3 points actually determine exactly where that line goes, because this is a hard margin constraint. Okay. But of course, you may be thinking that generally that's not possible, and indeed generally it's not. So this was a nice linearly separable example where it works to sort of impose, all right, let's find the best line that has the largest hard margin. But a lot of times you have some mix-up between your classes, and you can't perfectly separate them with the line. And so more generally, what you need to do is use a soft margin. So for data that's not linearly separable, such as the 2 moons data set, which we looked at for the KNN classifier, we can still do something similar. We just introduce a P. We penalize any points that are on the wrong side of the line. So it's okay if they're there, but we'll penalize it to try to get as good a classifier as possible. So we, instead of having a fixed constraint, we have a penalty for violating the constraint. And one of the typical loss functions that's often used for this is called the hinge loss function, and it's given by the following formula right here. Okay, so we're going to be looking at the maximum of 0 and 1 minus yi times inner product wxi minus b. And so if you look at that loss function for a second, think about, okay, on the right side of the line, okay, if I'm correctly classified, so I'm on the right side of the line, then you know, this will come out to be a 1 and a 1, then you're going to get a maximum of 0. You just get 0. There's no penalty. But if you're on the wrong side of the line, then the max will be from over here. And basically, the penalty will get larger and larger based on how far away you are from the separating line. So for example, if I go back up to this picture, if I had a white point, like close to the line, you know, maybe like right here, I wouldn't be penalized as much as if I had a white point, you know, all the way back here, which was really far from the line. That would be an even greater penalty. Okay. So this is how we penalize points that are misclassified. And we then solve the overall problem by fixing some parameter C and then minimizing the following objective. Okay, so we want to find the minimum over, you know, before we were just minimizing the norm of W subject to some constraints. But now we're going to minimize W squared plus this average penalty of misclassified points. Okay, so then a very important question comes in. How do you choose C? And that will have a big effect. So the parameter C determines how much we penalize points for being on the wrong side of the line. So if you think about taking C larger and larger, this will start to sort of dominate. So we want to really choose C in a smart way. And as we'll see later in the lecture and also in the homework, a good way to do this is through cross-validation. Okay, so let's take a look at an example. So let's look at, well, actually, let me stop and see if are there any questions on that yet? Okay. Then let's take a look at an example, which is support vector machines and the two moons. So remember, this is a very handy little function, which will just make these moons data sets for you. I used to write scripts to do that in MATLAB, and I didn't realize that there was one in Python that just did it for you. So that's cool. So we're going to take 500 points. We're going to specify a random state of 1. And you may notice in the homework, we ask you to do that on some of the problems too. That's just for reproducibility so that you can generate the exact same data. And with the noise level of 0.3. Okay, so then here we're just going to plot the data with a little scatter plot. So first we're going to plot the blue points, and then we're going to plot the red points. And this is the picture that we get, right? So we've got the blue and the red points that are not linearly separable with a bit of mix up and overlap. So now the one function that you can use to run support vector machines in Python is this SVM function, this svm.svc. SVC stands for support vector classifier. So here we can first define exactly what kind of model we want to use. end off with the linear case, so using the linear curve and choosing a C of 10. So first we define that we're going to do this type of SVM in the model, and then we fit the model to the data. So then we can do model.fit X, which is our features, and Y, which is our labels. And print model, you can see what kind of model we're using. Okay, so let's take a look now at how the classifier is performing. So let me scroll down here. So this is again just plotting the data, the blue points and the red points, just like before. But now we're going to add the predictions made by the support vector machine classifier. So here we're just defining our range of values, xmin to xmax. Ymin to ymax was perhaps an unfortunate choice of notation because this is not really y, it's not the labels, it's like x2, it's the second spatial dimension, but we define our range of values there, and then make a mesh grid of all the different, so we have a lattice point of values, and then we predict, we apply the model.predict function to all of these points. So what's happening in the code here is it's from the array of x values, it's making a long vector, and then it's putting it together in an array, dimensional array of points, and making the prediction on all of the points. And so then here you can see it's plotting the filled contours and also the contour lines. So this first call plots the shaded regions. So it's showing you that the classifier will define all of the points above in this light red zone to be the plus ones, and all of the points in the blue zone to be the minus 1 points. Okay, so it's actually not bad. Even though this data set has a highly nonlinear structure, still it's kind of able to cut through it in a way that that somewhat accurate for the data, but we'll see that we can definitely make it better. Let's take a look at the accuracy. So make the confusion matrix. So first we'll define a vector of all of the predictions. So you can use the model.predict function, apply it to all of our data points, which we stored in X. And then we can call the confusion matrix where we have our true labels given by the vector Y and our predicted labels given by the vector YPred. Okay, and then we can call the metrics.accuracy score to see what kind of accuracy we're getting. And here's the confusion matrix. As you can see, most of the points are correctly classified and the accuracy is about 86%. You can kind of read off the accuracy from the confusion matrix because the points that are correctly classified lie on diagonal. So the accuracy would just be the sum of the diagonal elements divided by the sum of all elements in the matrix, or use the accuracy score. Okay, and then we had a question. So in this example, you chose a C of 10. Why did you choose 10? Good question. So that was a bit arbitrary, right? I just picked something. And in general, you don't know. In general, you should choose this with a cross-validation procedure, and we'll show you code for exactly how to do that. But I just want to give you an idea of what it does and what it looks like for a fixed C. Okay. Okay, great. But before we do that, before we go into the choosing C and the cross-validation stuff, there's another aspect that I want to discuss first, and that was the fact that what we did so far on the moons was with a linear kernel. Okay, so this was a case of linear SVM, which is what I presented at the beginning of class. But a lot of times, if your data set is not linearly separable, it's helpful to apply a nonlinear kernel transform. So for example, if you had a ring of points and then another ring of points around that ring of points, you would totally fail trying to find a linear separator, but you could find a nice separating curve. So the algorithmic challenge here is to solve a more complex problem without increasing the computational complexity too much of the optimization problem. The basic idea is actually pretty straightforward. So the classifier we were dealing with so far, which is the linear SVM case, is the classifier where X is assigned to the sign of this line. The sign of inner product Wx minus B. But you can see, what is this? Well, Wx minus B is a linear function of X, but we could have chosen that to be a nonlinear function of X. So more generally, we can think about the general procedure as mapping X to the sign of f of X, where now f of X can be any function. It doesn't have to be a linear function. And when f is nonlinear, it will create nonlinear boundaries between the classes. So what are some of the options that you can choose? Well, the nonlinear transform options in scikit-learn are, first of all, there's the linear one, but then the nonlinear options are polynomial. So here you can, this is linear, but then you raise it to the d, which turns it into a polynomial of degree d. And then this one is very popular. This is called the RBF kernel, which stands for radial basis functions. This is kind of like a Gaussian kernel. If you've seen that before, maybe in some of your other classes. So you're looking here at an exponential function raised to e to the minus gamma times x minus x prime squared. I think the notation here is a little bit different than what we were using before because of to match the documentation for these functions. But think of this x prime as w, right? So that's just another way to write this vector of parameters, x prime or w. Okay, and gamma here is a scale parameter, which is quite important to choose that correctly to get good results. And as you can see, that comes in to a lot of these functions. And then the last one is a sigmoid function, which is defined by a hyperbolic tangent of a linear function. Okay, and then as I said, probably the most popular is RBF. So that's a good one to try. So let's try it on the same data set, just switching from a linear kernel to an RBF kernel. So once again, we'll call svm.svc with an RBF kernel and a C of 20. And here you can specify the gamma, which is this parameter right here. I think scale is the default scaling. So I think if you don't say anything, it'll specify to scale. And what that basically does is that parameter, according to a heuristic that depends on the number of features, the dimension of the data, and also the variance of the data. So there's some built-in heuristic for how to compute the gamma. Okay, and then once again, we'll fit X and Y. And then now let's take a look. Once again, we plot the data colored by class, blue and red. And then once again, we make our mesh grid of points and we apply the predict function to compute what class all of those points are in. And then we can draw with the contour functions, we can sort of, fill in the blue and the red regions and also outline in black the boundary between the two. Okay, and so you can see this is actually really nice. Now the boundary really kind of has that nice curve and can kind of follow that moon shape through the data. Okay, so let's see how the accuracy does. Once again, if we create the confusion matrix and the accuracy, we see a pretty substantial improvement to 91%. Okay. So what if you have more than two? So far we've been talking about, a separating hyperplane or curve. But how do you deal with more than two classes? Well, I'll say the method, I mean, you can't do it with more than two classes. The method just doesn't work. So there are generalizations that that apply to the classification problem with more than two classes, but they're built upon this binary case. And there's kind of two different ways to do it. First is the 1 versus 1. And in this case, what you do is you consider all pairs of classes. So if we have K classes, say we have 10 classes, then we have K choose 2 different pairs of classes. And for each pair, we can develop a classifier. Right, so we might have we might have class 1, and we might have class 10, and we might have a classifier that can tell us, are you class 1 or are you class 10? But we can do this for all pairs. So we end up with a bunch of classifiers. We have K choose 2 different classifiers. Then if we actually want to make a classification for a new observation, we just ask all of those different classifiers, and we choose the class which was most frequently assigned. Okay, so some of them kind of won't make sense, because if maybe we have class 5 and the classifier is distinguishing between class 1 and class 10. However, if it really is class 5, a lot of them will vote for class 5, and we should, at the end of the day, when we take a consensus over all of the different classifiers, we should see that a lot of them voted for, that the most frequent vote was for class 5. So that is the idea of looking at all classifiers based on all pairs of classes. But another way you can do it is the all versus 1. And so in this case, if you have K classes, then what you're going to do is you're going to make a classifier that compares each class to the remaining K minus 1 classes. So basically you would have a classifier that gave you an answer to the question, am I in class 1? Yes or no. And then am I in class 2? Yes or no. Am I in class 3? Yes or no. And to each of those answers, we want to assign a confidence level. We won't really go into the details of this, but the idea is that then we can make these K different classifiers, and we do all of them, and we can go with the answer where we sort of have the most confidence. I believe that the default in Python is this sort of first method. It's based on a 1 versus 1 procedure. Okay, so now let's look at another data set, which is the IRIS data set, which is one of the built-in data sets that's available. And so here, we've looked at this one before, but let's just do a little recap. It's a data set of containing 3 different species of iris. Iris setosa, versicolor, and virginica. And we have 4 features for each observed flower, which is the sepal length and width and the petal length and width. And overall, we have 50 flowers. Okay, so 50 data points, 3 classes, 4 features. Okay, and we want to figure out, we want a classifier that can determine what species the flowers are. Okay, so we have this data set built in Seaborn that we can just load it automatically. And then we can do the pair plot in Seaborn to visualize the data. And you may remember from when we looked at this before that two of the species have a lot more overlap than the other one. So the Setosa is pretty well separated, but there's a bit of mix up between the versicolor and the virginica. And so here we can see the scatter plots of all combinations of pairs of features. Notice here we got the petal length and the petal width actually seem to be a lot more helpful for distinguishing the classes than the sepal length and the sepal width. Okay, so we can also get the same data set from scikit-learn. And so let's take a look. Just so that we can visualize things really easily, let's just make it two-dimensional and just use the first two features here. Of course, you would not really want to do this in practice. You would want to use all of your features, so don't do this at home. Okay, but just so that we can visualize it, let's take the first two features of the data set as X and then our labels as Y. Okay, we can define color maps and plot the data. And since we're getting a little short on time, let me kind of go through this a little more. So we can see a plot of the data here and one that's well separated or kind of mixed up. Well, if we use the SVM classifier with an RBF kernel and a C of 3, same sort of default scaling for gamma, then we can fit this SVM model. And let's take a look at what we get. So now you can see that we get these nonlinear separating lines, just like we did with the 2 moons data set. There's still kind of a lot of mix up here, but it's doing a decent job given the amount of mix up in the data. Okay, and then if you compute the confusion matrix and the accuracy, you can see that the overall accuracy is 81%. And well, never mind, actually, let me not make that comment so that we have enough time for cross-validation. Okay, so in the last few minutes, let me go over cross-validation procedure, which you recall is a method for assessing how well a model lies to an independent data set. And the basic idea is that we split the data into training and test, train the model on the training, obviously, and then measure the accuracy on the test. And there's a few different ways to do this. And the one that we'll kind of in class is k-fold cross-validation. And this is where we randomly partition the data into k pieces. Those pieces are called folds. And then for each of the k folds, we train on the k-1 folds and test on the remaining folds, and we alternate which one is being used as the test set so that all of the points get to be one of the test points at some point during this procedure. Okay, the accuracy is then computed using each of the k folds as the test set. Okay, so let me go over what some of the functions are to support cross-validation with scikit-learn. So first, the train test split function can randomly split your data for cross-validation into training and test data. You have to tell it what portion you want to keep for testing, This is really handy. This cross-val score function is super easy to work with, and it automatically splits the data and measures accuracy on the test set. And this function has a built-in k-fold cross-validation procedure, but it does all of it behind the scenes. So you don't have to manually go through and define all the folds and keep up with the accuracy on each one. It will just, you tell it what you want to use, and it implements the cross-validation with k-folds and just reports the accuracy on the test, all of the different test folds. Okay, and you can also tell it what metric you want to use, whether that's accuracy or the F-score or some other things. And the cross-validate also is a little bit more general, so you can use this too. And the basic difference with cross-val score is that you can keep track of multiple metrics for evaluation. Maybe you want to keep track of both, you know, accuracy and your F1 score, or some other metrics that you want to keep track of. And it also will create a dictionary with the fit times and score times and a lot more data. So if you want to go more fancy and keep track of more things, this is good. If you want kind of the quickest, easiest one to run, then that's good. Okay, so let's take a look here. If we try to answer the important question of how do we choose sorry, well, we're not quite getting there yet. So first of all, let's apply the cross-val score function to our estimator to get a better idea of how the accuracy will generalize to the test data. Okay, and let's say we use 5 folds, and let's see what we get. So if we do this, we can see this is the accuracy on those 5 different folds, and we see it's working pretty well. And then here you can just see some example code with the cross-validate function that keeps track of more metrics than just the accuracy. Okay, and I guess, yeah, so okay, we've pretty much gotten through the end. I'll just say real quick that this is really handy to use for choosing model parameters like the C, right? That's an important one to know how to do. And take a look at this code. You'll want to do something very similar in your homework for your homework problems. Basically, you know, you define a vector with a bunch of different possible values, a huge range of values, and then you enumerate over all the different values, all the different possible values for C, define a model with that C, and then use the cross-val score to get an idea of the accuracy that you would expect on test data from that model, and then record the mean accuracy of those scores. Okay, so you can kind of see here that increasing that parameter C worked well up to a certain point, and then it started to decrease. So if we want to find the best C, we want to pick the C that maximizes the accuracy on the test data set, and that would occur around here. I've kind of zoomed in so we can see where this is happening, around a C of 7. Okay, so yeah, sorry, got a little rushed there at the end, but hopefully that, you know, is sufficient to answer your questions, and look through the code and the examples I think will be very helpful for your homework. Any questions? Okay, no questions, but some thank yous, which is nice. You know, I have little kids and I don't always get a thank you, so that's a treat. Okay. Okay, I have a slight question on the homework, if that's okay. Yeah, sure. Okay, well, I'll dismiss everybody who wants to leave. Have a great day. And yeah, what's the homework question? I mean, I don't have the homework open, but if it's a general question, hopefully I can answer it.
It's mostly general. I don't have it open either. But I was looking at it yesterday, and so we're classifying. I guess I didn't quite understand the I know it's like part one and part two, but the part one where you're the numbers, we're classifying the image of digits, right?
That's right.
Um,
The INFEST one.
so it's we're doing classification on the visual digits. It just is kind of it's like, what kind of things are we classifying for? Like, is that laid out in the? I guess I should reread it, but.
Oh, so yes. So your data points there are just images, right? Just pictures. And you want to know, is it a 0? Is it a 1? Is it a 2? Is it a 3? You know, for example, you might be interested in an algorithm that can do this automatically. Like if you're a bank and you want to like read people's checks and you want to like scan and know what they wrote, you know, what their handwritten numbers, you want to convert that to digital numbers. You know, to do that, you have to have a classifier that takes a little image of each handwritten number that you wrote and can say, okay, yeah, that's an 8, that's a 7. And some of them are easier, you know. Sometimes the 1s and the 7s are a little hard to distinguish because some people make their 1s with a little, you know, thing at the top. But that's the basic idea. That makes sense, like what the problem is?
No, that makes a lot more sense.
Yeah.
Now I just got to think about how I got to do that. But no, that helps a lot. Thank you.
Yeah. But in terms of the code, it's very similar to like the IRIS data set. You know, it's already more than 2 classes. It's already having multi-class SVM. And you don't have to do anything special on your end. You know, Python does all of that behind the scenes.
Yeah. Okay. Well, awesome. Thank you.
Yeah.
Hope you have a good day.
No problem. You too. Thank you. Okay. Well, if there aren't any other questions, well, everybody's gone. So extension on the homework until Monday. I'll see you guys later. Bye.